In this video, we're going to look at another rule we used in probability called the addition rule. Before we look at the rule, we need to understand the idea of mutual exclusivity of events. Two events are said to be mutually exclusive if they cannot occur at the same time. This would mean that they have no outcomes in common with each other. And so the idea of mutual exclusivity is a term that we use when we're talking about two events. So if in our sample space, which remember, sample space is the collection of all possible outcomes, we have two events, A and B. If there is no way for these to successfully occur at the same time, we say they're mutually exclusive. But for some events, depending on how they're defined, it is many times possible for them to occur at the same time. And that occurrence would be represented by the overlap of these two circles, right? The circles represent the collection of outcomes that satisfy the description of the event. And so there are certain outcomes which sometimes satisfy both A and B at the same time. If that is possible, we say that the events are not mutually exclusive from each other. Best way to look at it is through an example. So let's look at event A. We roll a 3 on a die. Event B, we roll a 4 on the die. Since there really is no way to roll a die one time and get both a 3 and a 4 at the same time, these two events would be mutually exclusive. If we wanted to represent these in a Venn diagram, my sample space here would consist of all the possible outcomes when I roll a single die. Now, the way they have this drawn over here makes it look a little bit deceptive because we're only talking about a single die. So for a single die, 1, 2, 3, 4, 5, 6 would be the sample space, right? These are the possible outcomes for rolling a single die. Event A would be represented by circle like this, and event B would be represented with a circle like this. These circles do not overlap, and so we would say, yes, they are mutually exclusive. Looking at another example, we could say that event A is randomly selecting a male student, and then event B is randomly selecting a nursing major. So picturing these, again, here's our sample space. Event A, we have the males. In event B, we have nursing majors. And we can see here, the overlap of these two circles would be male and nursing, or A and B. That's where we have the overlap of the two. Over here, these would just be only nursing majors. And over here, this would just be males with other majors other than nursing. For this one, our event A is described as a blood donor with type O blood, and event B is a female blood donor. So what we need to do is ask, is it possible for us to select somebody randomly and have them be a female blood donor who has type O blood? And of course, yes, that is a possible outcome. So we can have event B and event A could happen at the same time with a single selection. So we would say not mutually exclusive. So if there's overlap there, they are not mutually exclusive events. So this brings us to the addition rule. The first one is our general addition rule. And we say general because this could be used in any situation where if we want to know the probability that A or B occurs, then we're going to take the sum of those two events, the probability of the first added to the probability of the second. The last part here is minus the probability of A and B. This is the overlap of our circles, right? The times where they would overlap with each other, and what the probability of that overlap would be. And the reason why this is important is if I have event A here and event B here, if I count up the outcomes in event A and express it as a probability, and then I count up the probabilities in B and express that probability, there are events that I've counted twice. I've counted the events that are both in A and B twice. And so I've overcounted the actual number of outcomes. And so that's why we have to take the probability of A and B and subtract it. We subtract the overlap not because it's not a successful outcome, but because we've overcounted. We just want to take out the numbers that we have counted too many times. When they're mutually exclusive, the probability of A and B of them happening at the same time is 0. With mutual exclusivity, if they are not overlapping, then the probability they happen at the same time is 0. So when they're mutually exclusive, probability of A and B occurring is 0. And so even if I take that into consideration, I would still be just subtracting 0 there at the end. And so essentially, when they're mutually exclusive, it's simply the sum of the two individual probabilities. But the first one is what we generally want to go with or think about, because thinking about whether they overlap or not is essential, and just as opposed to just assuming they don't overlap. If they do not overlap and they're mutually exclusive, then we just know there's nothing to subtract. We haven't overcounted. So let's look at using the addition rule. We select a card from a standard deck. Find the probability that the card is a 4 or an ace. Or also is our key word here that we use the addition rule. Or suggests that we have options. In other words, as I write this out, 4 or ace, I know there are 2 ways for me to be successful, not just one. And that's why we're summing up their individual probabilities. I will be successful if I pick a 4, or I'm going to be successful if I pick an ace. If they can happen at the same time, and they do, then that's even better, right? I satisfied both of them at the same time. So or suggests that there are more than one ways to be successful. In this case, we can see that selecting a 4 or selecting an ace are mutually exclusive. So they're not overlapping. I can't select a 4 that's also an ace. So the and part is something I can just ignore. This is going to be equal to the probability of selecting an ace plus the probability of selecting a 4. The probability of selecting an ace is 4 out of 52. And the probability of selecting a 4 is also 4 out of 52. Notice that I don't have to change the sample space here because I'm only selecting one card. What we're doing is taking the probabilities and their possible outcomes and really counting. If I think about how many cards are in the deck that would be a successful pick, there's 8 of them there, the 4 aces and the 4 fours. And so this is not like when we had the and where we had to say, okay, we're going to select 2. So once I've selected a card, I have to take one out because there's fewer cards on the second draw. That's not the case here because we're only selecting one card. Here's another example. You roll a dice, find the probability of rolling a number less than 3 or rolling an odd number. So 3, actually I'm going to put less than symbol in front of that. So a number less than 3 or just something that's odd. Taking these individual, the probability of selecting or rolling a die and getting a number that's less than 3 and the probability of rolling an odd number. The probability of selecting something less than 3 you could either get a 2 or a 1, right? So there are 2 out of the 6 that would be successful rolls. The probability of selecting an odd when I roll is rolling a 1, 3, or a 5. And so that would be a 3 out of 6, or 50%. I'm leaving it as 6 just so that we can have common denominators here when we add. Now, the one thing we need to consider, so here's what I would get. I would get 5 out of 6. So are there ways that I've overcounted here in the situation? And here, when we think about the rolls that would be less than 3 or something that's odd, we see that there's an overlap, right? When I counted up the less than 3, there were 2 numbers, 1 and 2. And then when I counted up the odd, there were 3 outcomes that fit that description, 1, 3, and 5. 1 is a number that is both less than 3 and is odd. And so I overcounted when I counted the 1 twice, right? I counted it here in the numbers less than 3, and then I counted it here in the odd numbers. And so this is where we say we need to subtract out the probability that it's odd. Let's put that there, sorry. So we're going to put less than 3 and odd. Well, 1 is less than 3 and it's odd. And so I need to subtract 1 out of 6. There is one number, and it's a 1, that is less than 3 and at the same time is odd. So, but notice how subtracting that, I only subtracted it because it got counted twice, right? It got counted here for the blue circle and for the red circle. So by subtracting it once, I'm getting 4 out of 6, which is the correct count, which is 2/3. Notice that. How many numbers do I have? Well, there's 1, 2, 3, 4. There's 4 actual numbers that would be successful picks, and out of the 6 that are possible. And so 2/3 is actually the correct probability. 5/6 would have been much too high. So when we see this, the A and B, right? Event A and event B, you want to think of it in terms not of the multiplication rule, but of the overlap of the outcomes. And this is because we're only doing it once, right? So if we're performing a single trial like this, I'm not going to have one followed by another. But I have to think of it in terms of they have to happen at the same time. That's the interpretation of and in a single trial scenario. All right, let's look at some more examples here. Here we have the frequency distribution showing the volume in sales in dollars, the number of months in which a sales rep reached each sales level during the past 3 years. Using this sales pattern, find the probability that the sales rep will sell between $75,000 and $124,999 next month. So here's the probability I'm after, that the sales rep will sell between $75,000 and $124,999 next month. And we can see that that is actually 2 different rows here, this one and this one. So there's 2 events that comprise or describe what we're looking for here, 2 rows. If we consider those as 2 separate events, A being that's between $75,000 and $99,999, or $100,000 and $124,999 is event B, this would be the probability that either A or B occur, simply because they were just in different rows. And in this case, they're mutually exclusive. We can see there's no overlap there. Either you're going to fall into this category or you're going to fall into this category. So the probability of A plus the probability of B, we can think of the probability of A and B, but there's no way that that would happen. Well, the probability of A is 7 out of the total, which would be 36, because we're talking about months over 3 years, so 7 out of 36, plus event B would be 9 out of 36 minus, is there any way that these two overlap? Nope, they're not. So it's 0 out of 36. But at least you can see we considered that, right? We didn't just assume that there wasn't an overlap mistakenly. And that gives me 16 out of 36, which in decimal notation would be approximately 0.4444, or 44.44% probability based on previous sales. All right, below here we have the different blood types, O, A, B, and AB, and then whether they were Rh positive or Rh negative. Now, my nursing students out there, you can probably tell me what that stuff means. I don't really know, to be quite honest, what the Rh positive and negative are, but it doesn't really matter. I've got it all laid out here. The question that they want us to do with this information that we have is to find the probability that the donor has type O or type A blood. So O or A is the probability. We're selecting one donor. The probability they have O is going to be found here under the total. There's 184 out of the total, which the number of donors was 409. Plus type A, so this is the probability of O. Probability of A is 164 out of 409. Adding these together, that's 8, 4, 3, 348 out of 409. Are there overlaps here? Do I need to subtract? Is there a way to pick someone who is both O and A type blood at the same time? And the answer is no. This would be 0 out of 409. So my probability then, 348 out of 49. Taking it out to 4 decimal places would be 0.850 and then 9. We're rounding that last 8 up because there's a 5 following that 8. The next one says, find the probability that a donor that we select at random has type B or is Rh negative. So here we can see the Rh negative is this row that has a total of 65. And then type B blood is the column here that has a total of 45. So if I find the probability of B or Rh negative, this is going to be equal to 65 over 409 plus 45 over 409. I kind of did these backwards. This one actually was, where did I get the 64? That should be 65 out of 409. And this is the Rh negative. And the other one is type B. So I did this a little bit backwards from the order that they're in, but it doesn't really matter here. We're just adding. But did I overcount? And the answer is yes, I did. There's 8 that were counted in both row and column. So the probability of Rh negative and B is 8 out of the 409. I need to subtract it once because this contains that 8 and this contains that 8, so I've overcounted by 8, and so I need to subtract 8 to undo the overcount. The total of this then is 110 minus 8, so 102 over 409, which as a decimal, approximate decimal rounded to the 4th digit, 0.2494 or 24.94% probability. So when they're written in rows and columns like this, we call this a two-way table. It's very obvious to see the meaning behind our, literally we can see the overlap there, right, between the column and the row. So that's a great way for us to sort of see that and get a visual of what that meaning is, subtracting out the probability of A and B. So let's look at the summary of some of the equations that we have looked at so far. We start out with just the classical probability. And this works if each outcome is equally as likely to occur, right? Rolling dice, tossing coins, all those things, they're equally likely to occur. All we have to do is count the number of outcomes in event E, right? Whatever E is defined in being, and then we divide that by the number of outcomes that were possible in our sample space. Remember, the sample space consists of successes and failures. In other words, the event outcomes and the event outcomes that are the complements of the events, right? So it's like the event didn't occur. This is the sum of all the successes and failures in my sample space. Empirical probability, if we are simply basing our probability on the number of successes that we have out of the number of trials that were performed, which would be our A, kind of our sample space total. We're just going to say, okay, how many successes did we have out of how many times did we perform the trial? Also, every probability is going to be somewhere between 0 and 1. It's impossible to have a probability outside of that. And the probability of an event not occurring, we say E prime or not E, is going to be equal to 1 minus the probability of the event. Then we looked at the multiplication rule, which we really applies mostly when we have sequential events occurring, right? We have one event, then we have a second event. If the first event changes the probability of the next event, we have dependent events. And therefore, we need to change this probability based on how A affected it. We assume A happened successfully, so we adjust the probability of B, assuming that A occurred successfully. If they're independent, the occurrence of A doesn't affect B, and so it's really just a straight multiplication between those. Also, if two events are mutually exclusive, the overlap will be 0, right? They're separate circles, they don't overlap, so we don't have to worry about subtracting the probability of A and B. But here the probability of A and B is used to think about, can they occur at the same time, and what's the probability of that overlapping occurrence? Here they want us to use this information about the NFL rookies and a position of the 250 players who were picked in the 2016 NFL draft. And what we want to find is the probability that a randomly selected pick is not a running back or a wide receiver. Not a running back or a wide receiver. So if we look at just the probability of A, let's define A as being a running back. And we'll define B as being a wide receiver, just to make it shorter. The probability that we would pick A or B, that it would be either a running back or a wide receiver, we can look through here and we see there are 31 wide receivers and there are 23 running backs. So the probability of A, that it's a running back, would be 23 out of the 253. The probability it would be B, a wide receiver, would be 31 out of 253. And so we see the probability that it would be either a wide receiver or running back would be 54 out of 253. But this is not what they asked us, right? What they asked is that it's not this, right? That it's not either a running back or a wide receiver. So what we want to find is the complement of what we just found. In other words, we want to find the probability that it's A or B. A or B complement. So the complement of what we just found. In other words, we want to take 1 minus the probability that is A or B. For this, we want to take the count of all the players who are either that are not A or that are not B. Looking back, we could see that that's going to include everything on the outside of both of these circles. 54 of them are in the circles. So if we go 1 minus 53 out of 253, that would be 54. So I put 53. 54 out of 253, that's going to give me 199 out of 253. Which would be approximately 0.7866. So there's a 78.66% probability that it would a randomly selected draft pick would not be a running back or a wide receiver. I want to talk really quick about the difference between mutual exclusivity, which is something we took into account when we were looking at two events to see whether they overlapped, and two events that were independent. Remember the different definitions of each. Two events are said to be mutually exclusive if they cannot happen at the same time. This was especially important when we were looking at the OR rule, when we had we had a single trial with two events, two possible outcomes. We wanted to ask ourselves, is it possible that these two outcomes could happen at the same time? Which would lead us to overcounting my outcomes because we would count something twice. Independence is something we considered when we had sequential events. And again, I'm saying these as sort of generalities. Sometimes you can have independent and mutually exclusive with single trial and double trial situations. So let's look at some examples and we can determine whether they're mutually exclusive and or independent. For the first example, we say, let's say that two people are selected from a population. So we have more than one trial occurring. There's multiple selections. And we check their blood type. Event A is that the person has blood type O, and event B is the second person has blood type O. So we have to ask, in this scenario, with two people being selected, is it possible that they could happen at the same time, which would mean they're not mutually exclusive, or would these be mutually exclusive, meaning they cannot happen at the same time? Well, with two people being selected, we could definitely say that they could both have blood type O, right? So they are definitely not mutually exclusive. In this scenario, then, are they independent or dependent? In other words, if I choose the first person and they have blood type O, is that going to change the probability for the next person having blood type O? And really, when we deal with large populations, that would not be a consideration. If the first person had blood type O, the same percent of people out in the general population are still going to have blood type O for the second. So the probability would not change once we picked a second person. So in this case, we have a scenario where they are not mutually exclusive, our events, and they are independent. Moving on to the next one. A seminar consists of 5 male and 5 female students. 2 people are chosen at random. Situation A, person 1, or event A, person 1 is male. Event B, person 2 selected is female. Remember that, again, just like in the previous one, we're selecting 2 people at random. So is it possible for these to happen at the same time? Is it possible for the first person to be male and the second person to be female? And we'd say, yeah, that's definitely possible for that to happen. So they are not mutually exclusive in this case. The next question is, are they independent or are they dependent? If we know that the first person that we select is male, will that change the probability that the second person we pick is a female? And the answer is yes, it would change, right? Because we only have 10 people. There are 5 male and 5 female. So if on the first selection we know we've selected somebody who's male, that would change the probability on selection 2 that we would get somebody that's female. In fact, it would be more likely now, 5 out of 9, that we would pick a female. And so these two events are dependent. When it comes to this, right, because it's kind of a similar thing, we're picking people at random, right? But this is a large population versus a very limited population, where picking one person, having them meet the requirement, definitely changes the probability on the second one. Now let's look at a single trial. And this is where it gets a little dicey. But let's say we have a telemarketer and they are calling a randomly chosen phone number. So we are only calling one phone number. Event A is the person who answers the phone is a male, and event B is the person answering the phone is a female. Are they mutually exclusive? Can this happen at the same time? Can I call a random phone number and have the person answering be both male and female at the same time? And we can even say here that they identify as either male or female. Well, in this case, this would be a mutually exclusive, right? It's going to be one or the other. We can't have both at the same time. Let's just forget the scenario where we call our parents and they both answer on speakerphone, right? This is just a randomly chosen person. Usually one person picks up, right? So these would be mutually exclusive. And then the question is, are they independent or are they dependent? If event A occurs, does that change the probability for event B? At the beginning, we would say there's a 50% chance that this would happen, the person would be male, 50% chance that the person would be female. So if event A occurs on this one phone dialing, if the person answering is male, does that change the probability that it would be a female? And the answer is yes, it does. It changes because if we assume the person answering was male, if this occurred, the probability it's female then goes down to 0 because event A occurred. If the person answering was a male, then event B, that would be a female, goes from being 50% to 0. And so these two are considered dependent events. In fact, when we have two events that are mutually exclusive, it's also impossible for them to be independent. And here, disjoint is the same thing as mutually exclusive. So if they're mutually exclusive, then they cannot at the same time be independent. It's impossible. They have to be dependent. But here we saw 3 different examples. On example 1, we had it being not disjoint or not mutually exclusive, but independent. When we picked a random person from the population, it was possible for them to occur at the same time. So they were not mutually exclusive. I'm just going to put mutually exclusive here. I don't want to confuse you. Also, example 2, they were not mutually exclusive. They could happen at the same time. We could pick the first person and the second person, first being male, second being female. On the third example that we just looked at above, they were dependent, in other words, not independent, and they were mutually exclusive. They couldn't happen at the same time. So it's important to keep those two concepts in mind. The difference between mutual exclusivity, which we're usually considering in or type of scenarios, and independence, which we're really taking into considering when we're taking more than one thing from the population most of the time. So we have sequential events, one following another.